Section 6.1 and 6.2, the inverse trigonometric functions. So first things first, recall that there's these things called inverse functions. And if you're looking at the graphs of two functions that are inverses of each other, then they're going to be reflections across the line y equals x. And I'm really thinking about x cubed and cube root of x, or x squared and square root, but that's even a better example when comparing to the trig functions, because x squared and square root, if you look at those two functions, they don't look exactly the same. That's a good indicator of where we're going. Well, the deal is that inverses are going to have domains and range that switch with the domain and range of the original function. That is, if you have a initial function, or specifically the domain of some function f of x, then the domain of f of x is going to be equal to the range of f inverse of x, and the range of f of x is going to be equal to the domain of f inverse of x. And inverse trigonometric functions are going to be written in one of two ways. You're either going to use the same notation that we write when we write inverse, f to the negative first, but of course remember it's not a power. It's not a power. So this is just read sine inverse of x. The other way to write it is arc sine of x. So those are two different ways to write the inverse sine function. Well, inverse cosine function, or arc cosine of x, inverse tangent function, or arc tangent of x. Okay? Just different notations. They're completely interchangeable. If you like one over the other, write one over the other. It makes no difference. They are exactly the same. So then we're going to start with our sine function. Now, just for the sake of remembering, remember that the domain of the sine function is going to be what? Well, the domain is all real numbers, right? And then the range is going to be from negative 1 to 1. Okay. But then we reflect this function across the line y equals x. What happens when we do that? Well, if we flip it across the line y equals x, I claim we're going to get this image. Now, not the red part, the yellow part. And it continues forever in both directions. But there's a problem, and the problem is that we want an inverse function. This isn't a function. It fails the vertical line test, and so it's not a function. So what are we going to do? Alright, we're going to cut down to the smallest section that gives us this inverse property that we want, while making sure that we still have a function. And that's what this red is. And so from here to here, we're going to cut everything else except for that, and that's going to be the part that we call our inverse function. So let's look at it again. Well, when we have this, notice some things. Well, notice that what happens is remember that we swap the x and the y values when we deal with inverses, and so now our input values are really what we were thinking about earlier as the y values of our function, but now they're the x. And so the inputs of this inverse sine function are going to be from negative 1 to 1. But the outputs are going to be angle measurements, and that's going to be from negative pi halves to pi halves. Okay? So notice that that's what we've got going on. Now, in terms of our unit circle, what does that look like? Well, that really means that when we're considering our unit circle, we're really just going to be in quadrant 1 and quadrant 4 because we're between the negative pi halves and the pi halves stuff. So then we can talk about our domain and range of this function. Well, our domains and ranges do swap from the other, but now we have this added restriction so that we can make sure they're actually functions as opposed to just some graph. And so we know that when we consider our sine inverse function, what is the inputs? Well, the inputs are from negative 1 to 1, and specifically, really, those are the y values. And then the range is going to be from negative pi halves to pi halves. And once again, we're thinking about our angles of rotation. And so it is useful to remember that when we're talking about inverse trigonometric functions, the input of the trigonometric functions, the input of the inverse trigonometric functions is really the y or the x value, or whatever the definition was that we had for each one. So for sine, it's the y value on the unit circle. and then the output is specifically the theta based on the rotation between negative pi halves and pi halves. And so then we can evaluate our trig functions. So if you're looking at your unit circle and I want to know what is sine inverse of root 3 over 2, all you need to do is look at quadrant 1 and quadrant 2 and find where do we get root 3 over 2. Well, for what angle? I claim that the answer is pi thirds. And so sine inverse of root 3 over 2 is pi thirds. Input was the y value from the unit circle. Output is the angle rotation. All right. Then we have sine inverse of negative 1/2. Look at your unit circle. Now, if you're looking at your unit circle, then you can of course recognize that there's more than one place where the y value is negative 1/2, but we have to make sure we're in quadrant 1 or quadrant 4. And so what quadrant 1 or quadrant 4 are our only locations that are okay, and so if I've got sine inverse of negative 1/2, I've got to be in quadrant 4. Specifically, I'm between negative pi halves and pi halves, and so my output has to be negative pi 6. And so that's the only choice for sine inverse of negative 1/2. Then we're going to do the same thing for cosine. Here's our cosine function. We're going to reflect it over the line y equals x. Once again, we have the issue where we don't have a function unless we cut some pieces off. So we're going to choose that the piece that we want is this piece. Okay, that's the piece we're going to take. Then, what do we see? We see that that puts us in quadrants 1 and 2 when considering our unit circle. And therefore, we know that our answers are going to have to come from quadrant 1 or quadrant 2 or between 0 and pi. Those are always going to be our answers. And so, of course, our domain for arc cosine or cosine inverse is from negative 1 to 1 inclusive. And then our output values will have to be values between 0 and pi. If you ever answer a cosine inverse function with some value that's outside of 0 to pi, you're automatically wrong no matter what. So then cosine inverse of negative 1/2. Well, notice that because it's negative, that means we have to be in quadrant 2. And since we're in quadrant 2, we know that we're going to get 2 pi thirds. Then cosine inverse of root 2 over 2, well, that's going to be in quadrant 1, so that's going to be pi fourths. Then we look at tangent. So tangent, do the same thing. Reflect over the line y equals x. We get this, but not a function, so we got to do restrictions. So we're going to restrict it to between the centermost asymptotes. Okay? And so specifically, we're going to get this. That is, we see that our solutions are going to have to come from quadrant 1 or quadrant 4, just like sine. Now, this excludes pi halves and negative pi halves because, of course, these now horizontal asymptotes when considering the inverse tangent function. But regardless, we know where our answers have to come from. And then when we consider the domain and range, well, the domain of arctangent is all real numbers. You can plug in anything into tangent inverse. But the range is going to be values between negative pi halves and pi halves exclusive. That is, we do not include those endpoints. So you can't take tangent inverse of pi halves or tangent inverse of negative pi halves. So let's evaluate tangent inverse of pi thirds. Well, we're either in quadrant 1 or quadrant 4. So, of course, what's this going to be? This is going to be pi thirds, right? Because we're in quadrant 1. Then tangent inverse of negative 1. Well, because it's negative, that means we have to be in quadrant 4. But be careful because we need the negative rotation angle. So, that is, this is going to be negative pi fourths. And so that's our answer. Then the inverse reciprocal function. So how are these going to work? Well, realize they work like this. If I want to talk about cosecant inverse of some value, that's really the exact same thing as saying sine inverse of 1 over that value, right? Because remember that the inputs and outputs of sine and sine inverse and secant and cosecant and cosecant inverse are swapped. That is, in this situation, we're actually inputting the y values or the x values, depending upon sine or cosine, and then the output is an angle measurement. So, also secant inverse of x, well, that's really the same thing as cosine inverse of 1 divided by x. And then cotangent inverse is the same thing as tangent inverse of 1 divided by x. So this is probably going to be the easiest way to think those inverse reciprocal functions. Now, let's run through our domains and ranges of our inverse trig functions, because of course they've changed from what we're dealing with, so let's run through it. So the domain of sine inverse is going to be from negative 1 to 1, inclusive, including the endpoints. Our range, remember that's going to be quadrant 1 and quadrant 4. from negative pi halves to pi halves. Then cosine inverse, same domain, from negative 1 to 1, inclusive. But our range here is from quadrant 1 to quadrant 2, so that's going to be from 0 to pi inclusive. Tangent inverse has a domain of all real numbers. Anything you want to plug in, you can. But the range of tangent inverse is going to be from negative pi halves, exclusive. Remember, we don't include the endpoints here. For cosecant inverse, well, what's the domain there? Well, the domain is going to be from negative infinity to 1, from negative infinity to negative 1, union 1 to infinity, including the 1s and the negative 1. And then what's our range going to be? Well, it's the same restriction that we put on sine. And so that's going to go from negative pi halves to 0, union 0 to pi halves. Why is the 0 kicked out? Because remember that the 0 there is actually going to create a domain restriction for the original cosecant function, and so that's why that value gets kicked out. Secant inverse has the exact same domain as cosecant, and the range of secant is going to be the same as cosine, except for its vertical asymptote, which occurs at pi halves. Cotangent inverse is going to, of course, have the domain of all reals. And then we're not going to show it in picture form, but realize that if you were to do the reflection of cotangent like you did the reflection of tangent, you really want to take the best full between two asymptotes situation, and so that's going to be from 0 to pi, not including the endpoints. And so that's going to be the output of cotangent inverse. So now we're just going to find some exact values of expressions in radians. And the truth is all we really need here is our unit circle, and then we can answer our question almost fully. So, cosine inverse of root 3 over 2. Well, that's where is the x value, root 3 over 2. We know we're in quadrant 1, which is good. Specifically, our angle measurement is pi 6. Cosine inverse of negative root 3 over 2. We know we're in quadrant 2, and so that's going to be specifically 5 pi 6. Sine inverse of 1/2, we know we're in quadrant 1, therefore we get pi 6. Tangent inverse of negative root 3, well, that's specifically going to have to be in quadrant 4, but negative rotations, and so that's going to be negative pi thirds. Tangent inverse of 0, well, that's going to be 0. Cosecant inverse of negative 2. Now, if it helps, remember that cosecant inverse of negative 2 is the exact same thing as sine inverse of 1 over negative 2. Sine inverse of negative 1 over 2, what's that going to give us? Remember that because it's negative, we have to be in quadrant 4, negative rotation. Specifically, that's going to be negative pi 6th. Then, cotangent inverse of root 3 over 3. Once again, what's that going to be? That's the exact same thing as tangent inverse of 3 over root 3, or, of course, that's tangent inverse of root 3. And so that's going to be in quadrant 1. And so in quadrant 1, that's pi thirds. Alright, so now we're just going to find some approximate values. And so the beauty of this is that these are just calculator exercises. All you need to make sure of is that you are in the correct degrees or radians mode before you use the cosine inverse or tangent inverse functions. And so remember, all you need to do is find sine, cosine, tangent, hit the second button, and then the second sign will give you cosine inverse. Okay, so for the first one, second cosine is cosine inverse, and then type in negative 0.2689. We're going to round this to 2 decimal places, and we're only going to answer this in radians, so make sure you're in radian mode. Then our answer is going to be 1.84. Alright, well, what's tangent inverse of negative 0.2623? Well, calculator exercise, negative 0.26. Sine inverse of negative 2/3. Calculator exercise, that's going to be negative 0.73. What's cosine inverse of 1.318? Now, if you want to type it in your calculator, please go right ahead and check yourself. But I'm going to make an observation before we do anything. What is the domain of sine and cosine inverse? Well, it's going to be values from negative 1 to 1. And so the moment that we try to plug in a value larger than 1, I automatically know that that's not possible. There is no answer here. This does not exist, and so there's really not an approximation. There's just no answer. If we want to find the approximate value of a cosecant function, realize that all we have to do is understand how to rewrite it in terms of the sine inverse function. So cosecant inverse of 8.205, that's going to be the exact same thing as sine of 1 divided by 8.205. Well, then it's just a calculator value, and that is 0.12. Sine inverse of 3/5, that's just going to be approximately 0.64. Secant inverse of 5, well, let's rewrite it. That's really cosine of 1 divided by 5, and then a calculator value, 1.37. That's my approximation. Cotangent inverse of negative 2/3, well, that's really going to be the tangent inverse of negative 3/2, and then that calculator value is negative 0.98. Composition of trigonometric and inverse functions. And so it's important to realize that, remember that technically the composition of a function and its inverse, in general, f of f inverse of x, should equal x. And it should also be true that f inverse of f of x is also x. The problem is domains and ranges, and so we have to take into consideration domains and ranges of our inner and outer functions. Otherwise, this doesn't make any sense. So, the sine of sine inverse of x is x, as long as the x values are in the domain of sine inverse. Same for all the others. Cosine of cosine inverse is x, as long as x is in the domain of cosine inverse. Tangent of tangent inverse of x is x, as long as x is in the domain of tangent inverse. If you compose the opposite direction, you have to think about it slightly differently. Sine inverse of sine of x is going to be x as long as the x value is actually in the range of sine inverse. Because if not, you might have to take an extra step. Cosine inverse of cosine of x is x as long as x is in the range of cosine inverse. And tangent inverse of tangent of x is x as long as all the x's are in the range of tangent inverse. We're going to simplify each of the following as much as possible. It really means we're going to give an exact value. So, cosine of cosine inverse of root 3 over 2. Our question is root 3 over 2 in the domain of cosine inverse? Well, cosine inverse's domain is between negative 1 and 1. Root 3 over 2 is in there, so we're okay. And so cosine inverse of negative 3 over 2, take cosine of that, we're going to get root 3 over 2. Sine of sine inverse of 1.8, pause for a moment. Is 1.8 in the domain of sine inverse? No, because remember, we can only take values into the sine inverse that go between negative 1 and 1 inclusive, and 1.8 is outside, and so this does not exist. Tangent inverse of tangent of pi 6. Alright, so this is where we start having to be very careful. First question, is pi 6 in the range of tangent inverse function? And the answer here is yes. Because remember, we're in quadrant 1 or quadrant 2 or 4, quadrant 1 or quadrant 4. And so tangent of pi 6 is in quadrant 1, so tangent inverse of tangent of pi 6 is pi 6. Perfectly fine. Great. Okay. Sine inverse of sine of 3 pi fourths. Alright, what is our domain of sine inverse? What is our range of sine inverse? Our range of sine inverse is quadrant 1 and quadrant 4. It is from negative pi halves to pi halves. Is 3 pi fourths in there? The answer is no. 3 pi fourths is not in the range from negative pi halves to pi halves. And so because of that, the answer is not 3 pi fourths. So we do have to evaluate sine of 3 pi fourths. Well, what's sine of 3 pi fourths? Well, that's going to be root 2 over 2. Okay? But then the question is what is sine inverse of root 2 over 2? Well, that's in quadrant 1, specifically that's pi fourths. So we do have to be careful here, because it's not always true that the inverse automatically undoes the function. Sometimes you have to worry about domain and range problems. Let's do some more of these. Sine inverse of sine of pi twelfths. All we have to do is make sure that pi twelfths is in the range of sine inverse, and I claim that it is, so we get pi twelfths. Sine of sine inverse of negative 0.4, all we have to do is make sure that negative 0.4 is in the domain of sine inverse. We're good, so it's negative 0.4. Sine inverse of sine of 3 pi fifths. Okay, here we've got to be a little bit careful, right? So let's actually sketch this on our unit circle. Where's 3 pi fifths? 3 pi fifths is going to be over here somewhere. Alright, so this is problematic. Okay? 3 pi fifths. That's not in quadrant 1 or quadrant 4. So we have to do a manipulation. Alright, what do I claim? Well, I claim that what happens is that we actually need to use what's called the reference angle. So the reference angle is this angle. And if we were to reflect this ray across the y-axis and we use the reference angle phi, then we would actually get the correct angle there. And so if I do that reflection, well, let's do it real quick. Then it's over here. So then phi is here. And then this angle was still 3 pi fifths. But now I want to know what phi is. Well, phi is really going to be pi minus 3 pi fifths. And so that's really going to be 2 pi fifths. And so then I claim that our answer is actually 2 pi fifths. Alright, sine of tangent inverse of negative 1. For this one we just have to be a little bit careful. What is tangent inverse of negative 1? Well, tangent inverse of negative 1, that's going to be in the fourth quadrant. And so specifically it's going to be a reference angle of pi fourths, so it's negative pi fourths. So what's sine of negative pi fourths? Well, sine of negative pi fourths is negative root 2 over 2, because of course we're in the fourth quadrant. Then cosine inverse of sine of pi halves. Well, that's going to be cosine inverse of 1. And so then what is cosine inverse of 1? Well, cosine inverse of 1 is actually going to be 0, right? Sine of cotangent inverse of x over 2. Well, the trick here is a couple things. So first off, let's remind ourselves of the cotangent of theta definition. So using the unit circle, cotangent of theta was equal to x divided by y. Then also remember that if I have a statement, cotangent inverse of x over 2, what does that really mean? Well, that really means that cotangent of some theta is equal to x over 2. So then we want to superimpose this on our unit circle so that we can actually think about what's happening. Alright, so let's do that. Here we are. So let's pretend that I have some theta measurement. And specifically, if I'm using x over 2, then really I get this right triangle where my x value is x because we're told that x over 2, so I'm thinking x over y, and my y value is 2. Then I want to be able to find the radius. And so if I want to be able to find the radius, remember we can just use Pythagorean theorem. That is r squared is equal to 2 squared plus x squared. And so that's going to be r squared is equal to 4 plus x squared. Well then, I want to know what is sine of that same theta measurement. Well, specifically, sine of theta is really this cotangent inverse of x over 2 based on this picture here. And remember that our unit circle definition for sine of theta is really y over r. Well, what was our y value? Our y value is 2. And so I claim that the sine of this theta is 2 divided by the radius r, but we got to solve for the radius r, so I'm going to take the square root. And so specifically, that's going to be 2 over root 4 plus x squared. And that's our answer. That's the best we can do. There's not really much else we can do. Now this next one will clean up pretty nicely, I think. So if I have the cosine of tangent inverse of 3/4, I'm going to use the fact that tangent of theta is equal to y divided by x. Then when I superimpose on the unit circle, given some theta measurement, and I have 3 divided by 4, 3 is the y value, 4 is the x value, then I can find a radius where r squared is equal to 3 squared plus 4 squared, or r is equal to 9 plus 16. R squared, is equal to 25, and then r thus is equal to 5, and so I get r is equal to 5. Well then, when I'm trying to find the cosine of this theta that we just measured, because that's really what this statement says, what is cosine of theta? Well, remember that cosine of theta is really equal to the x value over the r value, and so that's going to be 4/5. And so that's our answer. And anytime they ask us to find the exact values, we still have to run through the same type of process. Superimpose it on the unit circle, make sure you're in the correct quadrants based on whichever inverse trig function we're using, and then evaluate tangent of that theta, or sine of that theta. Sine inverse of negative 2/5. Well, remember that our unit circle definition of sine of theta, sorry, not unit circle, but full circle, is going to be equal to y divided by r. Now, in this situation, this is really sine of theta is equal to negative 2/5, but I want to have a discussion about where the negative goes. Well, we're going to assume the radius is positive, and so that's going to be negative on top, so it's going to be negative 2 divided by positive 5, which means that we're really in quadrant 4. So there's some theta here with my right angle, where specifically I know that my y is negative 2, my r is 5. Then I can find the x value using Pythagorean theorem. X squared plus negative 2 quantity squared is equal to 5 squared. So that's x squared plus 4 is equal to 25, minus 4 minus 4. X squared is equal to 21. Take the square root, take the square root. X is then equal to root 21. Since 21 is 3 times 7, it won't factor. And so I get x is equal to root 21. Then I'm just trying to find what is the tangent of that theta measurement. Well, tangent of theta is going to be what? Well, this theta, remember that tangent is y divided by x, and so the y value is negative 2, divided by the x being root 21. And if someone asked us to rationalize, we could of course rationalize by multiplying by root 21 over root 21. That would give us negative 2 root 21 over 21. And so there we are. Then I want to find what is sine of cosine inverse of 8 over 17. Remember that our circle definition of cosine is x divided by r. And so therefore, my theta is actually going to be in quadrant 1 because I see that that's positive. And so I don't know what y is, but I know that my x is 8, my r is 17, and then I need to find the y value. So y squared plus 8 squared is equal to 17 squared. Y squared plus 64 is equal to 289. Minus 64 minus 64, we get that y squared is equal to 225. Take the square root of both sides. Square root of y squared is y. Square root of 225 is 15. Then I want to know what is the sine of this theta that we have just marked. And so that's really going to be, remember that sine is y divided by r, and so that's going to be 15 over 17, and that's our sine of theta, or specifically the sine of cosine inverse of 8/17. Alright, then we're just going to talk about some inverse functions. If I want to find the inverse function f inverse of f of x being equal to negative 3 cosine of x plus 2, how do we do that? Alright, so step 1, remember, swap your x's and y's. So f of x is really y, and so now this is going to state x is equal to negative 3 cosine of y plus 2. Then we're going to solve for y. So minus 2, that's x minus 2, is equal to negative 3 cosine of y. Then what happens? Well, we're then going to divide by negative 3. We then get x minus 2 divided by negative 3 is equal to cosine of y. Well, at this point, how do we solve for y? You take the inverse of both sides. So, take cosine inverse of this, cosine inverse of this. Well, I claim that now we have cosine inverse of x minus 2 divided by negative 3 is equal to y, which is our inverse function. F inverse of x is equal to cosine inverse of x minus 2 divided by negative 3. Now, to talk about the domain and range, there's a few approaches to go with here, but I'm going to claim that if we can think about the transformations done to the initial graph, and we can figure out what the range of this is, we already know what the domain is, which means that if we can find the range of the initial function, then I automatically get the domain and the range of f inverse. In fact, if we want, we can go ahead and state that because we know the domain of this initial function, negative 3 cosine of x plus 2, is from 0 to pi, we then know that the range of f inverse has to be from 0 to pi, which we kind of anticipated, right? We know that that's what the output's going to be. Now, how are we going to find the domain of this function? Well, I claim that the easiest way to find the domain of this function is to think about what is the range of f of x. Now, how do we know what it is? Well, first off, I see that the amplitude is 3. Because the amplitude is 3, I know that it has up 3, down 3. But we have to be careful because there's also a vertical shift up by 2. And so, what does that actually look like? Well, this midline here is at 2, and then up 3 from 2 is 5, down 3 from 2 is negative 1, and so I'm not even going to sketch the graph, but I know that this is going to vary between negative 1 and 5. And so I'm going to actually claim that the domain of f inverse of x has to be from negative 1 up to 5, strictly because we know that those are the outputs of negative 3 cosine of x plus 2. And so any of these others, just realize that if you think about what the range of the initial function is, that's exactly what your domain is going to be of the inverse function. And then we want to solve some semi-basic equations. I know you might be concerned because there are trig functions in here, but we're just going to do some algebra and then we're going to answer the question. So, if I have tangent inverse of x minus 5 tangent inverse of x, what's important here is to realize that tangent inverse of x and tangent inverse of x are the same. And so because they're the same, we can treat them like a single variable and combine like terms. And so look at the coefficients of those tangent inverse functions. Well, there's a negative 5 here and unwritten, well, there's a 1. So 1 minus 5 is negative 4. And so that's going to be negative 4 tangent inverse of x minus pi thirds is equal to 2 pi thirds. Alright, that's all fine. But at this point, then we just need to isolate our tangent inverse of x. So, let's add pi thirds. Add pi thirds. That's going to be negative 4 tangent inverse of x is equal to, well, 2 pi thirds plus pi thirds is 3 pi thirds, or pi. Then we can divide by negative 4, divide by negative 4. Tangent inverse of x is then equal to negative pi fourths. Alright? Now, if you don't recognize how to deal with this yet, understand that now that we have inverses, you can take the inverse of the inverse, which is just the tangent function, and you can take both sides of this with the tangent function. As long as our domain and range restrictions are fine, which I claim they're going to be, tangent of tangent inverse is just going to be x. And then x is going to be equal to tangent of negative pi fourths. Well, tangent of negative pi fourths is just going to be negative 1. And so then x is equal to negative 1. And so I claim we have now found x. Let's do it again, but for a sine function. So, once again, I see that there's a sine inverse of x, sine inverse of x. I'm thinking of those as my initial variable. I need to isolate the sine inverse of x. And so I'm going to pick a side to put all the sine inverse stuff on. How about we subtract 2 sine inverse of x, subtract 2 sine inverse of x. That's then going to be 3 sine inverse of x minus 2 pi is equal to negative 3 pi. Then we're trying to isolate that sine inverse of x, so how about I add 2 pi, add 2 pi. That's going to be 3 sine inverse of x is equal to negative pi. Then I can divide by 3. divide by 3. Let's be careful here so I actually get that inverse there. So then that's going to be sine inverse of x is equal to negative pi thirds. Once again, if you're not entirely sure, realize that you can just take the inverse of the inverse, which is sine of both sides. So then what happens? Sine of sine inverse of x, we're going to say is x, and then that's going to be equal to sine of negative pi thirds. Sine of negative pi thirds is negative root 3 over 2.